how many did you print out on this one?
Pardon me?
How many?
20.
20? And you know the rest was that right?
Sure.
Again, just pass these out. Thank you.
During a lesson that is 20 minutes or 25 minutes, that is really designed to be a 40-minute lesson, each of you who is presenting a lesson can, and I spoke to Doug about it, so he knows all about it. You can just go time out. Normally, I would be giving a 20-minute cooperative learning, but we only have a short amount of time, so I'm giving a 10-minute group activity. You can't do 10 problems if you only have 20 minutes. So you give 2 problems and say normally I would be giving 10, which would be appropriate for reinforcement. Okay?
I'll also just say now that it is going to be a shorter lesson because I have time, you know, a shorter amount of time, so that's why there are less questions on this. I'll just say that now, so I won't say time later. And we don't have any dry erase markers, do we? Oh, that's a Sharpie.
Yes. Oh, yes, you do.
For you? Where are you? Where are you? Where are you finding them? You put them in, oh, they're in your bag.
Yeah, there's also a black one up there someplace. The black one works better, the green one doesn't. He's got another black one, not the one I was thinking of. Try that one. That one. Good.
Okay.
Here you go. All right, all right.
Just reinforce.
Trick or treat, I want to see if you were awake.
I'm gonna set a timer on my phone too, so that way it'll be about 20 minutes. Okay. Morning, guys.
Morning.
So, as I'm pretty sure some of you guys know, in costume, today is Halloween. So are you guys gonna go trick-or-treating tonight?
Yes.
Yeah? Alright. So, maybe you've come across the same dilemma that I come across when I go trick-or-treating is I don't get enough candy. Sometimes I have to go and I have to grab another bag, have to dump my candy stash. Now, me, being as important as I am, teacher and all, time is of the essence. So I want to make sure I can get as much candy as I can in as little time as possible. Just like that. So, actually, it brings me to my point. So, I'm with my friend Mike, and we decided we want to figure out a way to get more candy in less time. Now, we were trying to think of a few ways. If it was you guys, how would you guys go about getting more candy in less time? Anybody have any ideas?
Maybe split the block in half and divvy everything up at the end.
Alright, that's a good idea. Anybody want to add on to that or have any other ideas as well? Okay.
Get in shape before Halloween.
Run to the houses faster?
Yeah.
That is an idea. So, kind of to put the two ideas together a little bit, we were thinking, what if me and my friend Mike each grabbed one more person? So that way, like you said, we would divvy it up and we can run to more houses. But we're greedy kids. 4 kids just isn't enough, right? So, how would we go about, in the same fashion, getting more candy? What would each person have to do in the group? Right, they would bring one more friend. So, it was me and Mike originally, right?
Mm-hmm.
And then me and Mike each brought one person. So how many does that make total?
4.
Right. So, if each of us, again, everyone in the group brings one more friend, how many would that be total?
8.
Okay, now, candy hungry kids. Do you think 8 kids will have enough candy? Or do you think we'll need more candy to split amongst each other?
Okay,
More candy, exactly. So, what do you think we would do?
get more people.
Yes. So each of us would bring one more person. So, if we each grab one more person, how many, after 8 of us, how many would we have?
16.
Right. Okay. So now we've got 16 kids scavenging the neighborhood for candy. Alright, so that should be, we're happy with 16. We're gonna leave it at that. Because after that, we're gonna start fighting each other for almond joys. Okay? So, now that we have that figured out, that is actually the start of our topic for today. It's going to be introducing powers and exponents. Now, what we just did was essentially using exponents and powers to solve our problem. So, first we started with me and Mike, right? So we have, we'll say 2. We have both of us right here, okay? Then what did? Each of us grabbed one more person, right? So, that became 4. Then what did we do? Grab more, and it became what? 8. And then of course 16. Now, to get from here to here, it was 2 and we brought 2 more, right? So what did we do? We doubled. So what's that called? When you, not adding, but multiplying, right. So, we did 2 times 2 to get to 4. Okay? And then we had 4, we did the same thing, right? We multiplied, everyone brought 1 more, so we doubled it. And we got 8, and then of course the same thing to get to 16. Now, between 8, 4, and 2, we see a pattern. Everything is being multiplied by 2 to get to that point. So we had 2 times 2, we can write that right down here like this, 2 times 2. And then this is 2 times 2 as well, right?
Yes.
So it's safe to say, if we multiplied 2 times 2 down here, we would get that as well. Now, if we went to 8, we multiplied by 2 one more time. Did I do that right? 2 times 2. There we go. Oh, I was messing myself up. So 2 times 2 to get to 4, and then 2 to get to 8, and then 2 more to get to 16. Now, that's a little bit easier than trying to figure it out this way. It's a little bit shorter. So, what do we see here? We have a common base. Now, 2 is going to be considered a base, and it occurs, how many times does 2 occur in this little set right here?
4.
4 times. Right. So that's going to be called our power. It occurs 4 times. Our power represents how many times our base occurs, our common base occurs. So, if we write it in the power format, which, if you guys skip ahead to the second page, I have a little notation right there. It gives you a quick little thing. It tells you about exponential notation. 2 is our base, 4 is going to be our power. And that takes us to 16, because it's 2 4 times. 2 times 2 times 2 times 2 gets us to 16. Okay? Alright, let's go over some examples other than this one. Okay? Now, on the first example we see, we've got 4 as our base, correct? So now we have 4 as our base. What would be our power?
7.
Right, 7 would be our power because it occurs 7 times. So, how would we write it? We'd have our 4, right? Now where would we put our 7? Up here?
Yes.
Okay. That's going to be our answer. So 4 times 4 times 4 times 4, 7 times is going to be written like this in exponential notation. Okay? Now let's give it a shot the other way around. Because now we know 4 times 4 times 4, 7 times will give us 4 to the 7. Okay? Now, on number 2, it's giving us the exponential notation. Now, how would we write that out? How would we expand 6 to the 9? First, let's let's recognize what is our base. Where is our common base?
6.
Okay, so we know 6 is our common base. So it's going to be 6 times 6 times 6, correct?
Yes.
A certain number of times. Now, what is our power that identifies how many times our common base occurs?
9.
9, right. So we know that this happens 9 times. Okay? So now if you ever see it, you guys can go back and forth. Now, that makes things a little bit clearer, a little bit easier. We've got examples 3 and 4. Is anybody comfortable enough to try out number 3?
Sure.
Okay, Raquel. Number 3. We have,
Our base is gonna be 7/2,
okay,
and then our power is gonna be 21,
right. So where will we put our power?
top right.
Correct. So, this is the same as writing 7/2 21 times. And that's a little bit easier, right guys? So I just saved you guys a lot of hand cramps. Raquel did as well. Okay guys, now number 4 is going to give you a few hand cramps. We won't write out every single one, but let's give it a shot anyway. So, who wants to try number 4 out? Okay, so, we've got number 4. Our base, what's our base?
3.
And our power?
30.
Okay, so how would we write that? How do we expand this?
3 times 3 times 3 times 3, 30 times.
Right. Okay. Has everybody got that? Anybody have any questions on not sure about this? Okay, I'll take your signs as an okay. Alright, let's go to the next page, guys. Now we're going to take it a step further. Now, you guys saw, you multiply things a certain number of times, and you can write it as an exponential form, right? Now, everybody knows, has everybody experienced before when they multiply 2 negatives together, what do they get?
Positive.
Right. Now, what happens if you multiply a positive and a negative together?
Negative.
Correct. Okay, so, looking at this, when an exponent is even, so what does that mean? If we have an even, if our power is even, so if we have 2 to the 4, what does that mean about 2? How many times do we multiply it?
4 times.
4 times, and 4 is an even number, right?
Yes.
So we have an even number. So what would happen if this was a negative 2?
It would still be an even number.
Right, so this would be multiplied an even number of times, right? So what does that mean about our product?
It's going to be even.
Be positive, correct.
Positive.
So, when our exponent is even, our product is going to be positive. So you guys good? Write that in, so you guys have that notes for later. Okay? Right there you see as our example. So you guys can write in right there, it's going to be positive. Okay, so, given that example, when our exponent is odd, just like when we're multiplying normally, what happens to our product?
Negative.
Right, so if I change this to a 5, and I added that one extra negative, it was originally positive, right? We know that this becomes positive, but it's a positive times a negative. So our answer will be negative. So that means when an exponent is odd, our product is going to be, class,
Negative.
there you go. Okay, so let's do an example. Now, sometimes things can be extreme, sometimes they can be small. If we have -5, 17 times, let's first, what is our base?
5. Negative 5.
Okay, -5 is our base. And what does that make our power?
17.
Okay, now what do we know about the number 17?
It's odd.
Okay, so what does that mean about our product?
It's going to be negative.
Okay. That's pretty straightforward, see? It follows that same pattern, okay? Whenever the exponent is going to be even, it's going to be positive. Whenever it's going to be negative, whenever it's going to be odd, it will be negative. So keeping that in mind, let's try number 2. Okay? Now it's going to be multiplied a lot of times. It's going to be negative 1.8, right? 122 times. Now, what do you think is going to happen at the end of that 122nd time being multiplied?
It'll be positive.
It's going to be positive. You guys sure?
Yes.
Now, why do you think it's going to be positive?
Because 122 is an even number.
Correct. All right, fantastic. Now let's go to the next page, guys. Okay. Now, the next step, we're identifying right now what these are called. These can also be called monomials. Okay? It's a number or a variable, or a product of a number, and it has one or more variables in it. So right now, we're looking, actually, screw myself up. Okay. So, we're looking at the monomial. So, 3 squared would be a monomial in our example. And 3 to the 4th would be our monomial as well. So, we're looking right here. It's going to give us an example about one more rule we can partake in. So, we know when we multiply powers with the same base, we can add their exponents. So, when you multiply the base, you add the exponent. So, looking at our example, we have 3 squared times 3 to the 4th. Okay? So, our bases, are they the same?
Yes.
Okay. But our exponents are different. Right. Okay, so how would we expand this? What would it look like if we wrote the whole thing out? Rico?
We'll do 3 times 3
Mm-hmm.
times 3 times 3 times 3 times 3.
Now, sometimes you may lose count of that, right? If you want to write it too many times. So, what's a shorter way of writing this? Since we know, because of this rule, when you multiply powers of the same base, you can add their exponents. Well, how can we write this? Anybody have an idea?
3 to the 6.
3 to the 6th? How do you get 3 to the 6th?
4 plus 2.
4 plus 2? Okay, so how would you write it?
Three.
Before you got from the 3,
3 to 2 plus 4 as the exponent.
like that?
Yeah.
Okay. Does everybody see how we got to that conclusion? Okay? Because if we look at this right here, we've got 3 squared, 3 to the 2, right? And then we have 3 to the 4. So, it's 2 here, and then 4 here. And it's just adding them, so it's 6 times overall. So, we have 3 to the 6. Alright, is everybody clear on that one? Anybody need me to go over it one more time? Okay. So you can use, as I wrote, you can use a rule right there. It'll work on every situation. So if you guys ever get stuck, you ever see an exponent that's really big, or an exponent that's really small, you can use this. When it's the same base, A will be our variable, and we'll use B and C as our exponents. So if you have A to the B times A to the C, it's the same thing as saying A to the B plus C. Okay, so that'll work if you put 5 here, if you put 10 here, if you put 1,000,000 here, that'll still be the same. And if B and C, they could be the same number, they can be a different number, it'll still function the same way. So it's an overall rule for anyone to use. Okay, so let's keep this rule in mind, and let's try the first example. Who thinks that they may be a little bit comfortable enough with this to try this first example? Okay, so let's do number 1. So, what do we have? We have 2 to the 4.
4 times 2 to the 1st.
Okay, so how would you go about solving this?
I would add the exponents, and the base would remain the same 2 to
Okay.
the 5th, or 4 plus 1.
Like this.
Yes.
Okay, so does everybody see the step that she used? to use this right here. So A to the B plus A to the C. In this case, our A is our 2, our B is our 4, and our C is our 1. So we combine them together right here to get our final answer. Okay? So let's try one more before we head off to something a little bit more tricky. Put that up there. Let's try number 2. Gabriel, you've been a little quiet today. Let's give you a shot at this. Alright? So, how would you go about solving number 2?
4 to the 3 plus 3.
Alright, and then what would you get as your final answer?
4 to the 6.
4 to the 6. Okay. Does everybody see how we got that? Nice and clear? Alright, fantastic. Now, things get a little bit trickier because we've been working with addition. Now, when you add a positive and a negative together, it's essentially finding the difference. So if you add 5 plus a negative 3, what would be the answer?
2.
2. Okay. Because what happens when you take negative 3 from 5, you're going to get 2. Just like if I had 5 M&Ms, and he ate 3 M&Ms, I'm only stuck with 2 M&Ms for myself. That's why I took this whole bag. Alright, so let's keep this in mind. Now let's check out the next question. Okay? So, we've got number 3. Who knows what our base is in this one? Anyone can shout it out.
5.
5. Okay, so we know 5 is our base. And then our exponents are what?
5 and negative 3.
Okay. Now, how would we write this out using the formula that was given to us before?
5.
Okay.
5 plus negative 3.
Okay. Now, does that still work for this?
Yes.
Right, just like I said, guys, remember, it'll work for any situation. So, like our example before, we found out that 5 plus negative 3 equals
2.
2. So that is going to be our answer. So, not every time, though, will our exponent be positive. We have to take that into account. Okay, guys? Let's take a look at number 4. Alright? We have our base. It's going to be 3 negative 4 times 3 to the square. 3 squared. Oh, I didn't even get like halfway through. I took way too much time.
Just do the ticket out.
Do the ticket out? Okay. Alright, guys. On the last page, we have our candy conclusion. Now, we found out that by squaring and then doing to the third and to the fourth, getting 16 of us all together. In this example, I even went one step further, there were 32 of us. So, let's correct a little mistake, put 15 instead of 31. Okay? So, basically what I want you guys to do, since we found out that if we did 2 times 2 times 2 times 2 a certain number of times, we would get to 16. How many, where was it? Alright. Yeah. If I wanted to receive 10 pieces of candy, and I can only get from half the kids, because I only like Reese's, and each kid, let's say they only got 1 piece of candy. Yeah, I don't want to make this question again. Okay, that makes sense. I read it again. Okay, so first I want you guys to determine the power that the base 2 needs to get to in order to get the total number of kids that we have out going trick-or-treating. After you find that out, I want you guys to determine the number of pieces of candy that I get to eat all by myself. And that's really it. So if you guys want, give that a shot. Any questions on that?
You said there were 16 friends?
It was 15 friends, so it would be one including myself, so it's 16 altogether. And since we actually don't have any time, I'm gonna have to stop you right there. Alright, so, let's go over it. Do I go over the ticket now?
No, no, that's fine.
That's fine? Okay, so,
They all have the answer anyway.
alright.
No, what's the final answer?
Okay, so, basically, it's a little bit tricky. I made it a little bit harder. So instead of saying there were 16 altogether, I said 15 friends, so you'd have to include me to make it 16. So, 2, we found out would be raised to the 4th power to get 16 kids altogether. Okay? And then I found out that I would only want to get candy from half the kids, so it would be half of 16, which would be 8. And then it'd be 10 pieces of candy from each. So it'd be 8 times 10. I get 80 pieces of candy. Okay, guys? So the trickiest part of that,
Didn't you have to find out what power two is?
right? Basically,
Oh, you don't wanna know the power of what, how many pieces of candy? I thought
no,
that
no,
was
it's
what-
basically it's determine what power 2 is raised to. If I was able to get 15 kids.
Oh, okay.
Yeah, 15 trick-or-treaters. So the trickiest part was realizing that there weren't just 15, there was actually 16 of us all together. So it would actually be 16. That was the hardest step. After that, simple division and multiplication. And since at this point the kids would be at that level at 8th grade, they'd be able to do division and multiplication. The trickiest part was finding out that was actually to the 4th power.
The way I read it, I thought you wanted to know what the power of how many candies you had.
Oh.
Like 2 to what power would equal 80, and
I see.
So
I'm sorry
that's-
about that. I'm sorry I wasn't clear.
Oh, no, that's.
Okay. Comments? Strengths, what did you really like about it? Yes?
I really like the opening and just applying Halloween to how to show exponential growth by showing. you know,
Perfect timing, Halloween and candy, go for it. What else?
Oh, I do have candy.
Yes, Tom?
I thought he did great, I thought he was very comfortable and he knew what he was talking about, and I think that's important, that's what I always struggle with. That's the content, if you know it, it gives you more confidence.
He's very comfortable and well-informed about his content. Yes?
He also made it very, he broke it down to make it very simplistic, so it was very easy to understand even if you don't know math.
The scaffolding throughout the lesson was excellent.
Yeah.
He kept bringing it from a lower to a higher concept and reinforcing it constantly throughout the, albeit abbreviated, lesson.
Good.
What else?
Second thoughts.
How about voice projection?
Excellent. I thought he was great.
It was even, consistent, and very good. Very appropriate for this size classroom and the number of people in it. What else? Yes?
He wasn't just staring at the
Yeah, she
board,
described
came
it.
in contact with us and kept
I'm
us
good.
involved.
Right. He used the board very well, and he didn't get fixated on the board. He was really working the room, the crowd.
You can have that back there.
What does he have to improve on? Come on, we all have reason to improve.
Thanks.
Timing piece of it, he had a lot more to do, and,
Pacing.
yeah.
He would have to, even though this is a demo lesson and we all understand those constraints, which are unique, the pacing would have to be adjusted. And sometimes you can't do every example. Oh, my favorite.
I heard you say it. Okay.
Pacing is something that we all have to work on all the time. And it's particularly important with the upper grades, because sometimes the kids will ask us a question, and the way I go off on a bird walk and I'll tell you something that's interesting and I believe to be germane to the point, you still have to keep coming back as quickly as possible to your content. Because the illustrations might, be amusing, but they are not necessarily expansive relative to what you're presenting. I wrote a couple of comments, I just said, okay. He used very well, and you did not have it on your strategies, you used choral responses where everybody had to respond. That was excellent. And then you went to individuals. So you're going back and forth between individual and choral response. Choral response is the whole choir is doing it at once. That's where they get choral from, okay? Another strategy he uses, by doing this, by giving you this, he saved you, and it's called advanced notes. He saved you from having to write down all of the equations. You had it there, so you could concentrate on his solving it, or your solving it. Rather than, I mean, can you imagine if you had to write down all of these things? Like he puts it on the board and you have to write it in your notebooks, it would never happen. That's why advanced notes, when you consider them carefully, are fantastic, because they particularly help at-risk, high-needs children.
Yeah, so I was gonna say it's type of adaptation, correct?
Yes, it is. It's a very good
If
adaptation.
you're not able to like write yourself or.
Yeah, and building on what you just said, you're not insulting the higher level, higher performing child in your class by giving out advanced notes, because they're going to add more to it than anybody else in the room. But you're giving the poor needy kid a real jump start, so he or she can concentrate on what you're saying, and that he or she can hear what you're saying, rather than, how much do we hear when we're down like this, right? When you have your head down, you're not seeing the board. And some kids are compulsive about getting every single thing down. Do not erase the homework assignment, so they write down, do not erase the homework assignment. Because they think that's a note. They're not even reading what they're writing. That's sad. So when you give them advanced notes, you put the homework assignment at the end, and it makes it so much easier for them, because then they can concentrate on what's being presented. How do you pronounce, and I'm not the math person, so who
No,
else
I
is?
got it too,
You said monomeal.
Monomial.
Monomial.
Mono.
Mono.
Monom.
Monomial. It's pronounced monomial.
It's mono, monomials.
Is it pronounced as if it's M-E-A-L?
Yes, it is.
Oh, yeah.
Monomial.
Oh,
Yeah.
I thought it's monomial.
I thought it was monomial.
When I went to school, it was monomial.
Yeah, I thought so too.
Poly-
Somebody Google it and hit speak. Go ahead.
Monomial. Monomial. I say monomial.
Monomial, polynomial.
Polynomial.
Yeah. Yeah.
Okay.
That's funny, because I put that too, I had never heard it pronounced that.
Oh.
Serious
Yeah.
days.
It's an adaptation for the teacher.
Okay.
Okay.